In this video, we are going to motivate the process of definite integration as a means of finding the area under a curve, and we'll have a brief look at how to use definite integration to calculate the average value of a function. If you aren't already familiar with indefinite integration, which is the reverse of differentiation, then you should watch my video What is Integration before this one. Consider a function y equals f of x plotted in the xy plane. Suppose we want to calculate the area under this curve between two x values. Let's take the ordinates x equals a and x equals b and denote the area under the curve between a and b as capital A. Now consider a point on the curve between a and b with coordinates x f of x, and consider a small increase in x, which we denote delta x, here using the lowercase Greek letter delta, and consider the corresponding incremental area delta A. If delta x is small, then delta A is approximately the area of the rectangle with height f of x and width delta x, i.e. delta A is approximately equal to f of x times delta x. Thus, delta A over delta x is approximately equal to f of x. If we take the limit as delta x tends to 0, we have dA by dx equals f of x. This means that A is the integral of f of x with respect to x, which we can write as g of x plus a constant c, where g of x is the function that differentiates to f of x. In other words, d by dx of g of x equals f of x. G of x is thus the function we would obtain from indefinite integration applied to the function f of x. However, what we're looking for here is numerical values, not a family of solutions, so we need to establish the specific function that this describes. We have to find the constant c. To determine c, we use the fact that when x equals a, the area, capital A, equals 0. Thus, we know that g of a plus c equals 0, yielding c equals minus g of a. Substituting c into our expression for a gives us the area as a function of x, which equals g of x minus g of a. Thus, the area we're trying to calculate, which lies between x equals a and x equals b, corresponds to the value of this function at x equals b. Thus a is equal to g of b minus g of a. This tells us that the area under a curve between two limits can be obtained by integrating the function, substituting in the upper and lower limits in turn and calculating their difference. This process is called definite integration. We write this as the integral between limits a and b, which you can see are written either end of the integral sign, of f of x dx equals g of b minus g of a, where d by dx of g of x equals f of x. Remember that definite integration generates a numerical value as the result, whereas indefinite integration provides a family of functions as the result. Okay, so let's look at an example. Here we have the quadratic function 3x squared minus 4x plus 7, and we are integrating between limits 1 and 3. That is, we are evaluating the shaded area shown here. First, we perform the integration itself. As with indefinite integration, this is a matter of doing our reverse differentiation on a term-by-term basis. Integrating 3x squared gives us x cubed. Minus 4x integrates to minus 2x squared, and the constant 7 integrates to 7x. We thus have the function g of x equals x cubed minus 2x squared plus 7x. It is worth noting again that, unlike indefinite integration, we don't need to include a plus c constant term in the integration, because we are going to put numbers in for x. In this case, a equals 1 and b equals 3. If we did add a constant to the function g, it would appear in both g of b and g of a and would cancel out, since we subtract g of a from g of b. The way we write this is as shown here. Notice the notation used. We have square brackets with our integrated function g of x inside the brackets and the limits 1 and 3 written outside the brackets. Now we need to subtract g of 1 from g of 3. The convention is to write this stage as a pair of curly brackets as shown here. Finally, we do the calculations. We have 27 minus 18 plus 21 minus 1 minus 2 plus 7, which yields 30 minus 8, and the integral equals 22. That is, the shaded area equals 22. We note again here that performing definite integration has generated a numerical value, unlike indefinite integration, which generates a formula that describes an infinite family of functions separated by constant values. Let's do one more example. Here we are asked to find the area under the curve y equals sine theta for theta between 0 and pi radians. Let's have a look at what that looks like. So, the area A equals the integral between 0 and pi of sine theta d theta. First we integrate. The integral of sine theta is minus cos theta. Then we put in the limits, giving minus cos pi minus cos 0, which is minus 1 minus 1, giving 1 plus 1, and the area in question is 2. Let us consider again a curve in the xy plane described by the equation y equals f of x. To find the average value of the function between a lower limit a and an upper limit b, we first look at the area under the curve, which is, as we have seen, the definite integral of f with respect to x between a and b. We can generate a rectangle that spans a to b and has area equal to the area under the curve, as shown here. The y-coordinate corresponding to the top of this rectangle is defined to be the average value of the function over the interval x equals a to x equals b, which we denote here as alpha. Then, alpha times the width of the rectangle, which is b minus a, equals the area under the curve, i.e. alpha equals 1 over b minus a times the integral between a and b of f with respect to x. Let's do an example. Here we are asked to find the average value of sine theta between 0 and pi radians. In this case, alpha equals 1 over pi minus 0 times the integral between 0 and pi of sine theta with respect to theta. Well, we already did this integral before. It had the value 2. Thus, the average value of sine theta between 0 and pi is 2 over pi.